Okie dokie. So I'm doing a new recording because I did annotate these notes. Just not annotate, but I added a few things. I added a few things that you may want to add to your notes. The biggest thing that I've added is this paragraph that is right here. So if the substitute teacher would press the enter button on the doc cam, it will pause the video for students to write down the notes. Go ahead and press enter now. Coming back, the only other thing that I had added was this thing right here where I underlined this and I added the word rationalize next to denominator. I don't think we need to pause the video for that at all. Okay, so let me go back to the top and explain what we wrote down. I know that a lot of you in my first period class, you're used to me asking you questions with your partners, but remember when we go back in time, I used to just lecture from here and record and upload. I need to do that too sometimes, just to make my videos better from last year, especially when I change things. So here we go. What we're going to start doing in section 4 is what happens when you try to square root a negative. In the previous sections, I said it's no solution. Well, that's really not the case. It's no real solution when you try to square root a negative. The reason why it is no real solution is because when you try to square root something, what we're saying is what times itself equals a negative 1. And there's nothing that exists something times itself equals a negative 1. There's no real number that happens. So what a mathematician decided to do a long time ago was, what if we invented something where if you squared it, it would equal a negative 1, an imaginary unit. Like something times itself is going to equal negative 1. And you have to think to yourself, that's impossible, because a positive 1 times a positive 1 is a positive 1, and a negative 1 times a negative 1 is a positive 1. And the only way to get to a negative is a positive times a negative is the only way to get to a negative, and it's not something times itself. It doesn't exist. That is why a mathematician invented it. What if we created a definition that says this will be an imaginary number and this times itself will equal negative 1. And we can do a whole lot of problems that are based off of this definition. You guys need to know that I is the same thing as the square root of negative 1. Anytime you see the square root of negative 1, that is going to simplify to I. I squared will always simplify into negative 1. It will just pretty much multiply to be negative 1. So what we're going to be doing is we're going to be dealing, how do we deal with imaginary unit I, and what do the problems look like? Well, let's give you an example. This is the reason why I included this example in here. Using I, we can now simplify radicals to have a negative radicand. Earlier I told you can't square root negative 16. Because nothing times itself equals a negative 16. But what if I were to think about it in terms of what I just told you? What if I said this is square root of 16 times the square root of negative 1? I bet you could do the square root of 16. If you know what the square root of 16 is, go ahead and say it out loud. 4. And I just gave you a definition of what this is going to simplify to. The square root of negative 1 is going to simplify to what? Say it out loud. I. So guess what this simplifies to? 4i. That's going to be our imaginary answer, 4i. Thank you. So I wrote down this little shortcut because I will rarely break it up into these two pieces to do the problems. A lot of times I go like this, and I'll take that square root of negative 16. I'll just take this square root of a negative, and I'll pull that thing out, and I'll just go like that. And then 16, I know goes like that. And then I can pull out the 4 right there and go 4i. So you're going to rarely ever see me do this, but this is how we're supposed to do it. That's the full long way. This is how I normally will do it, and you guys can do it this way as well. When you go ahead. Okay. So before you even begin the problem, you have to deal with that square root of a negative first, and then you can do the rest of the problem, just so you know. And once you have that, basically everything else is just like imaginary numbers are like square roots. So if I have, let's say, 1 plus 2i, and I want to add 3i to it, 2i can combine with the 3i. 2i plus 3i is 5i. And you cannot add the 5i with the 1 because they're not like terms. Only the i's can combine with other i's when we're adding and subtracting. Adding and subtracting, roots can only be added to their same roots, and you just add the coefficients. If we're multiplying, that's a whole nother thing. We're going to talk about that in a second. But when we give our final answers, we always give the real component first and then the imaginary component second. That's what this is, a plus or minus bi. Our final answers should have the real component first and any imaginary numbers second. The last thing that I have up here is, what do we do since sometimes square roots are in the denominator? I taught you how to rationalize square roots. Well, what if there is an I in the denominator? That means you have a radical in the denominator. You're going to have to rationalize, just like you would what we did in previous sections. It's like unit 0, I think it is. If the denominator is a monomial, you're just going to multiply by I, meaning one group of multiplication. If it's a binomial, we have to multiply by its conjugate. If you do not know what the word conjugate means, it means the same binomial with a different sign in the middle. I'll give you an example. If I have 2 plus I in the denominator, the conjugate would be 2 minus I over 2 minus I. You have to do the same thing over itself. You take the object, the binomial, and you change the sign in the middle. If it was 2 minus I, the conjugate would be 2 plus I. Now that we have that, let's go through some examples together. This is in your notes packet, so please write them down as we go through it. It says the square root of negative 192. Okay, well, you can't square root a negative, but we're going to use imaginary numbers now. If I do this and go like that, that's going to simplify to what? Go ahead and say it out loud. Good. And then you have to deal with this root 192, which I know that 2 goes into there 81 times. Is that right? No, that's not right. 96 times, thank you. And 96 can be divided by 3, 32. And 32 is a 16 and a 2, and a 4 and a 4. I could break the 4s down, but I'm not going to, because I already have a pair. Anytime I've split it, I don't need to use it anymore. So I have a pair of 4s. It's going to pop out. Pair of 2s, it's going to pop out 4 times 2 times I, and then there's this 3 that's all by itself inside the radical. My final answer, numbers, then letters, then radicals. 8i root 3. 8i root 3. Is that what you got? Perfect. You're going to be doing several of those kinds of problems. Not harder. Other kind of problems that you're going to have to deal with is how do I deal with imaginary units I, and remember they can only combine, add, or subtract with other i's. 9 plus 11i, if there's nothing in front that needs to multiply in or exponents outside, we don't need those parentheses. But if you have a subtraction sign in front of your parentheses, it means you're subtracting or doing the opposite of adding the 6 or subtracting the 6. Instead of subtracting the negative 7i, we are now subtracting it, which is adding 7i. And then we can combine our imaginary components and we can combine our real components. Let's put this in standard form. Let's do the real components first. 9 minus 6. Let's do the imaginary components. 11i plus 7i is? And this is in standard form. Real component, imaginary component. A plus bi. That's what that means. I want to check on my first period class. If you understood what we just did and you feel like you know what you're doing based off of what I've shown you, give me a hands up so I can see how many are understanding. Perfect. Thank you. That helps me. Helps me know. Number 12. Things change when we multiply, though. This is where this is going to get a little more challenging, but not much. If you see 5 minus 2i in parentheses squared, it means 5 minus 2i times another 5 minus 2i. That's nothing new. Foiling is nothing new. 5 times 5, bless you, is 25, bless you. 5 times negative 2i is negative 10i. Then inside times inside, negative 10i again. And then the last times the last is a negative times a negative, which is a positive. 2 times 2 is 4. I times I is I squared. Something's going to happen with that. So right now, these two things will go together. They're the same sign. They're both negative. They add to negative 20i. But something happens with this 4i squared. Anytime you get I squared, I told you earlier that that simplifies to something. It simplifies to negative 1. But what that means is it's 4 multiplying the I squared. It's 4 multiplying a negative 1. What does that do to the 4? It turns it into a negative 4. So a lot of times what you'll see me do is you'll see me move this over here and put negative 4 over here with that 25. 25 minus 4 is 21. And now I have it in standard form. Real component, imaginary component. My answer, my final answer is 21 minus 20i. My word of caution to you is this right here is where some students forget. 4i squared just changes the sign of it and it turns it from an imaginary component into a real component. Not too difficult though once you realize it, okay? I have, oh my, I didn't even know that was down there. Okay, here we go. I got number 20. There is an imaginary unit I in the denominator. I can't leave this with the square root in the denominator. So what I need to do is I need to follow these quick directions. If it's a binomial, I need to multiply by its conjugate. And we're going to do the same thing over itself. If it's 3 minus 2i, the conjugate would be But we can't just multiply by 3 plus 2i. We have to multiply by that over itself. When you're multiplying this times that, you need to know that this line means that this is a group. And this line means that that is a group. Don't forget that, because in actuality we are foiling both of these numerators and denominators. It's almost like two separate problems. So if we do the denominator first, this is going to show you why we did the conjugate. What is 3 times 3?
9.
3 times a positive 2i is plus 6i. What about the negative 2i times 3 is what?
Negative 6i.
And what about negative 2i times a positive 2i would be?
Negative 4i.
Okay, so that's just my denominator. I have not done the numerator yet. Now the whole reason I'm going to just pause right there on that part is because the 6i and the negative 6i gets rid of that. And we talked earlier about what happens with this I squared. So what happens with this negative 4? Does it stay negative 4? What's it going to become?
Positive 4.
And that now is a real component. This is going to become a positive 4 because this is a negative 1. Let me cross that off. That makes that a positive 4. So the 9 plus 4 makes... Does your denominator have an imaginary component anymore in it? So that is why we multiply by a conjugate. You can think of it as a difference of squares for imaginary numbers. And because the difference of squares is going to get that I squared in it, it will then turn into a real component for our denominator. But that's not what's going to happen for our numerator. Our numerator, on the other hand, let's work this out. First times first, negative 3. First times the outside, negative 2i. Inside times inside, plus 15i. Last times the last. 5 times 2 is 10. 10i squared. Let's do the imaginary component first. 15i minus 2i. 13, Mr. Paramo. 13i plus 13i. The I squared and the 10 makes it a negative 10, which can combine with the negative 3. Negative 10 minus 3 is negative 13. This is where it is good for us to remember what we did with the quadratic formula. Remember how we split it? They're both being divided by that denominator. Negative 13 is being divided by 13. And the plus 13i is being divided by 13. That way you can reduce, because this denominator goes into both parts of the numerator. This simplifies to negative 1 plus I is our final answer. So the last thing I need to talk about before I end these notes is about how to graph complex numbers. Complex numbers can be graphed by the real component and the imaginary component. The real component, remember how earlier I told you that this is the real component? That's your x-axis. That's your real axis, is left and right. This is your imaginary component. Instead of going up or down by 1 and 2, and 3. We go up by 1i and 2i and 3i and down by negative 1i, negative 2i. Our y-axis then becomes the imaginary components. So if I were to try to graph negative 1 plus I, I would go to the left 1 unit and up 1i unit. It'd be just a dot right here, just so you know. The only other thing that these questions are going to ask you is how to graph or figure out what the absolute value of a complex number is. If you want to know what the absolute value of a complex number is, it's its distance from the origin in the complex plane. So if I have 3 minus 2i and I want to know 3 minus 2i, what the absolute value is of it, you do a squared plus b squared and take the square root of it to find that distance. Think of it as the triangle right here. The absolute value is this distance. I'll show you an example below. Plot each number in a separate complex plane, then give its absolute value. I'm trying to select this guy. I don't know if it'll let me do it. Let me grab it from here. Perfect. There we go. That's what I'm trying to do. Plot each complex number on a separate complex plane. Okay? So this is your real component. This is your imaginary component. This is your real component. I have to go how many? 8 units to the left. 1, 2. Do you have to draw 8 lines? No, just go, okay, 8 units to the left. My imaginary component is negative 6i. Means we go down 6i. 1, 2, 3, 4.
Were you anything with talking?
No, thank you. Love it. Love it. 1, 2, 3, 4, 5, 6. 6i is right here, negative 6i. So here's negative 8, here's negative 6. This point right here is the point negative 8 minus 6i. That's how we plot it. We plot it as a dot. It's a location. Then it says give its absolute value. So if we went to the left 8 units and we went down negative 6i units, if we find this distance, we'll know what the absolute value is. If I want to know what that is, what I'm doing is I'm treating it like it's a triangle, a right triangle. We're going to use the Pythagorean Theorem. I'm going to do a squared plus b squared equals c squared as a distance. So we're only really going to focus on the positive distance. I don't need to worry about negative distance here. Negative 8 times negative 8? 64. If you're confused by this, the I is not going to matter here at all. 6 times 6 is 36. If you're thinking, oh, what about the I squared and it makes it negative, don't get bothered by that at all. When we square it, this looks like it's supposed to be, hold on, I got to do something real quick. It's just distance. It's just distance. Yes. Don't get confused by this I squared. Don't turn that into a negative. Don't do that at all. We're just looking at the distance. 64 plus 36. Square root. Square root. The absolute value of negative 8 minus 6i is going to be a distance of 10. Based off of the definition in our textbook, which talks about distance being the Pythagorean theorem. I'm going to stop your notes right there, and then I'm going to